Hi, Assalamualaikum, salam sejahtera, and salam I love UPM to all professors, doctors, dearest colleagues, and to those who are watching this video right now. Before I go any further, allow me to introduce myself. My name is Mohamad Alif. I'm from Kuala Lumpur, and I'm currently a master's student from UPM Bintulu. And in this video, I'll be sharing my small contribution on the chemical modification of reduced graphene oxide for electrochemical application.
So, my project is titled Facile Preparation and Characterization of Oxygen-Rich Reduced Graphene Oxide for Improved Electrochemical Performance. Now, let us begin. At the turn of the 21st century, global warming has become one of the main discussion topics with growing concerns over the effect of greenhouse gases on the rising global temperatures.
Well, one of the major contributors to greenhouse gas emission is the burning of fossil fuel. Vroom vroom. Thus, climate change prevention policies have been introduced during the UN Climate Change Convention to enforce countries and corporate businesses alike to take action against this problem, which has significantly boosted the innovation in green technology.
Recently, we can see a growing trend in the usage of electric vehicles. The major leap in advancement of lithium-ion battery was a keystone innovation for this trend.
Hey, this is all good news. However, there's no such thing as a perfect technology, as there are still potential improvements to be made as more and more discoveries are reported in the scientific community.
Graphene is a revolutionary material which was first reported in 2004 by a research group led by Novoslav and Jem from the University of Manchester. Ever since its successful separation, the hype of graphene boomed due to its extraordinary properties. But despite its hype, graphene-based technologies are still almost non-existent. Why is that?
This is because the manufacturing process of graphene is very expensive and complex. So, where do we go from here?
Well, we have reduced graphene oxide. Reduced graphene oxide, or RGO, is a cost-effective material with similar exciting properties to graphene, and the main difference between the two is the presence of oxygen functionalities on the carbon layer. Various reduction techniques have been introduced to minimize the oxygen content in RGO, such as thermal, chemical, electrochemical, and plasma treatment. However, a debate ensued pushing the need for some amounts of oxygen functional groups to be present in the final product for electronic and energy storage applications. This previous study had been introduced to tune the oxygen functionalities on RGO. However, these works use toxic reagent and energy intensive treatment to tune the degrees of oxidation in RGO. This is where I established the research question for my work. I asked whether or not there is some other way to avoid the use of acid, base, or toxic reagents to control the degree of oxidation on GO without the use of an energy intensive treatment. Previously, Chen et al. Studied the effect of KCl addition during chemical reduction of RGO for supercapacitor application. The authors found that KCl interacted with RGO and produced chemically modified RGO with a higher carbon to oxygen ratio. However, in another study, using potassium hydroxide to modify RGO, the authors found that the chemically modified RGO had a lower carbon to oxygen ratio and proposed that potassium ions can prevent the removal of oxygen functionalities. Hence, the research objective for my work were to investigate the effect of the amount of KCl added toward the degree of oxidation in GO during the chemical modification step and evaluate its electrochemical performance as an electrode material using cyclic voltammetric analysis. This is the simplified process for this work. The synthesis of chemically modified RGO began with oxidation via modified Harmus method. Next, we have the modification step where KCl was added into a graphene oxide or GO suspension. Two masses of KCl were used in this work, 3 grams and 5 grams of KCl, which are named 3SGO and 5SGO respectively. Finally, the GO samples were reduced using ammonia to form RGO. UV-Vis and FTIR analysis were used for the material characterizations of all GO and RGO samples. The electrode performance were analyzed using cyclic voltammetry analysis of 3 electrode system with drop-casted glassy carbon as working electrode. And now I will move on to the findings of my work. Shall we continue? GO and RGO were successfully synthesized, evident from the UV-Vis absorbance spectra. For GO, the UV spectra showed a strong absorbance at 2 to 9 nanometer with a broad shoulder peak at 278 nanometer for all synthesized GO. These peaks corresponded to the aromatic C-C and C-O respectively. After reduction, peak shifts were observed for RGO and 3S-RGO from 2 to 9 nanometer to 257 nanometer, which confirmed the successful reduction of GO. This peak shift is due to the restoration of conjugated pi-to-pi bonds between carbon. But for 5S-RGO, the peak at 2 to 9 nanometer did not shift. It was only significantly reduced, which confirmed the reduction of 5S-RGO, but it is incomplete. Moving on to FTIR analysis. In all GO samples, we can observe that hydroxyl, carbonyl or carboxyl and epoxy groups were present as shown in Table 1. I also quantitatively analyzed the different oxygen functionalities present in all the GO samples. Table 2 simplified the calculated peak areas for each corresponding oxygen groups. The FTIR spectra showed a significant reduction in transmittant intensity between GO and RGO samples, which confirmed the successful reduction of RGO and 3S-RGO. However, again for 5S-RGO, it showed an incomplete reduction with major transmittant intensity were only partially reduced. When comparing Figure 2 and Figure 3, two opposite trends can be established. Firstly, for GO, the trend in calculated peak areas for oxygen functionalities is in descending order from GO to 5S-GO. For RGO, an opposite trend is observed where the degree of oxidation is in ascending order from RGO to 5S-RGO. Thus, there are some degree of interaction between potassium ions and oxygen functionalities which prevented the removal of oxygen during chemical reduction. And finally, we have the cyclic voltammetry analysis. The CV curve can reveal the behavior at the electrode-electrolyte interface. In Figure 4, RGO and 3S-RGO had an ideal rectangular-like curve which exhibited the typical electrostatic double-layer capacitor or EDLC. For 5S-RGO on the other hand, it showed a quasi-rectangular curve which revealed a hybrid behavior combining EDLC and pseudocapacitor. 5S-RGO had the larger CV curve. From the CV curve, we can also calculate the specific capacitance using the following formula. The calculated specific capacitance for RGO, 3S-RGO, and 5S-RGO is 5.93, 7.65, and 18.02 farads per gram respectively. Again, 5S-RGO had the highest specific capacitance value.
To summarize the finding, incomplete reduction of chemically modified RGO was successfully achieved by varying the amounts of KCl added during the modification step, which proved that potassium ion can prevent the removal of oxygen functionalities. From the CV analysis, we can see that 5S-RGO had the best electrode performance.
These were the references used in this presentation. We've come to the end of my video. Thank you so much for watching.
Goodbye.